Hello everyone, this is Rojalyn and in this video I will be explaining crystal field theory and color of the transition metal complexes. Before introducing the topic, I'll throw some light on the colored transition metal compounds found in nature. The green pigment of green leaves, that is called chlorophyll, is a coordination compound of magnesium. Similarly, the red color of blood due to the presence of hemoglobin, that is the coordination compound of iron. Similarly, in gemstones, these are colored due to the presence of trace amount of transition metals in their crystal structure. Why we see color? When a sample absorbed in the visible region of electromagnetic spectrum, then some of the light is absorbed and some of the light is transmitted. The transmitted light strikes our eyes and we observe the color, and that color is the color of that substance. If the sample absorbs all wavelength of visible light, then the sample appears black. Similarly, if the sample does not absorb in the visible light, then the sample appears white or colorless. The coordination complexes are colored due to two regions. One is DD transition, another one region is charge transfer absorption. What is DD transition? Before explaining DD transition, we should know splitting of d orbitals. In a free metal ion, all the 5 d orbitals are degenerate. Degenerate meaning is all are equal in energy. In octahedral crystal field, 6 ligands approach to the central metal ion, causing the change in energy in the d orbitals. Because the electron in the d cell and the electron clouds of the ligand repel each other. Some of the d orbitals gain in energy and some of the d orbitals lose their energy. The orbitals pointing directly towards the axis are affected mostly by the electrostatic interaction, and these are the dz square and dx square minus y square orbitals. Here, d orbital split into two sets of orbitals, that is T2g and Eg sets. The energy of Eg set of orbital is increased because dx square minus y square and dz square orbitals are pointing towards the axes. The energy of T2g set of orbitals decreases because dxy, dyz and dzx orbitals are not pointing towards the axes. They are present in the planes. The energy difference between the T2g and Eg set of orbitals is 10 dq. Here del O is the crystal field splitting energy in octahedral crystal field. The Eg set of orbitals are repelled by an amount of energy 0.6 del O or 3 by 5 del O. The T2g set of orbitals are stabilized by 2 by 5 del O, that is 0.4 del O amount of energy. In case of tetrahedral crystal field, the d orbital split into two sets, that is E and T2. Here the G term is not used because in octahedral complexes center of symmetry is present and in tetrahedral complexes it is not present. The splitting pattern in tetrahedral crystal field is just opposite of octahedral crystal field. The T2 set of orbitals are repelled by 2 by 5 del T amount of energy and E set of orbitals are stabilized by 3 by 5 del T amount of energy. Here del T stands for crystal field splitting in tetrahedral crystal field. The relationship between del O and del T is equal to 4 by 9 del O, that is equal to 0.45 del O. The magnitude of energy in case of tetrahedral crystal field is almost half of the magnitude of that in octahedral crystal field splitting energy. So the question is, why coordination complexes are colored? The coordination complexes are colored because they absorb in the visible region of electromagnetic spectrum. When the d orbital of the coordination compound is not completely filled, it is possible to promote an electron from lower energy d orbital to higher energy d orbital by absorption of a photon having an appropriate energy. Electromagnetic radiation in the visible region poses the appropriate energy for such type of transitions. The energy gap between the Eg and the T2g orbital is the crystal field splitting energy, that is the energy equal to the energy of a photon. Del O is equal to h nu, that is equal to del E, that is equal to Sc by lambda. As del O varies, h nu will also vary and the color of the compound will also change. For example, copper 2 complexes are blue in color in the solution. The reason is when copper 2 salt is added in water, an octahedral hexaco copper 2 complex is formed, which absorb in the red, orange or yellow region of the electromagnetic spectrum, and green, blue or violet light will be transmitted. That is why copper 2 complexes are blue in color. The color of the complexes can be easily predicted by using the color wheel. If the complex absorbs in the red region of the visible light, then the sample will appear green, as the green is the complementary color of red. Copper 2 complex contain 9 electrons in the d orbital. When it absorbs a photon of light, the electron jumps from T2g orbital to Eg orbital and the transmitted light is observed as the color of the compound. Color of the complexes depends on nature of the metal and nature of the ligand. Crystal field splitting energy depends on oxidation state of the metal, nature of the d orbital used in the complex, coordination number or geometry of the complex. As we all know that color of the complex depends on the crystal field splitting energy. So if the splitting energy changes, the color also changes. For example, chromium complexes in +2 oxidation state is blue in color, and in +3 it is green, and in +6 it is orange in color. So the color is different for the same metal with different oxidation states. When cobalt is in +2 oxidation state in the complex hexaco-cobalt 2, the color is pink, and when cobalt is in +3 oxidation state, the color is brown. Again, with changing in geometry, the color also changes. For example, cobalt in octahedral geometry, or when the coordination number is 6, its color is pink, and when the coordination number is 4, or when it is in tetrahedral geometry, the color is blue. Color of the complexes also depends on the nature of the ligand. Some ligands only produce a small energy separation among the d orbitals, while others cause a wider band gap. Ligands that cause a small separation are called weak field ligand, and those cause a large separation are called strong field ligands. The arrangement of the ligands in accordance of their splitting ability is called spectrochemical series. For example, cobalt, when it is in +3 oxidation state with different ligands, it will show different colors. Let us take some example. When fluoride is the ligand, as you know that it is a weak ligand, the splitting will be less. Here you can see in the diagram that the gap between T2g and Eg is very less. The observed light will be in the wavelength around 700 nanometer, and the color of this light is red, and the color of the transmitted light, that is green, which is the complementary color of the red light. When fluoride will be replaced by the ammonia in the same complex, the color will change to orange because ammonia is a stronger ligand and the splitting energy will be more. So the absorption will be in the smaller wavelength in the electromagnetic spectrum, and the transmitted color will be in the higher wavelength. In the same compound, when ammonia will be changed by cyanide, the color will be pale yellow because of the same reason, as energy is inversely proportional to the wavelength of light. Without any DT transition, some of the complexes are colored because of the charge transfer absorption. Charge transfer absorption or charge transfer spectra are of two types. One is metal to ligand charge transfer spectra, that is called MLCT, and another one is ligand to metal charge transfer spectra, that is called LMCT. For example, in potassium permanganate, there is no DD electron present in manganese, still it is colored. Because in case of KMnO4, the oxidation state of manganese is +7 and it is highly electron deficient, so electrons from oxygen will flow to this, and this is the reason why it is colored. Similarly, in strong ligands like carbonyl, cyanide and pyridine, they are having pi antibonding orbital, so excess electron from metal d orbital will flow to this antibonding pi orbital, and this is called MLCT absorption. The observance of metal complexes can be recorded by using a UV visible spectrophotometer. In this instrument, we can know the lambda max value, means the maximum wavelength where the compound will absorb. Here I want to conclude by saying that most of the transition metal complexes are colored. Crystal field theory provides the explanation of color of the complexes. When the d orbital is not completely filled, it is possible to promote an electron from lower energy d orbital to higher energy d orbital by absorption of a photon of electromagnetic radiation having an appropriate energy. This appropriate energy often possessed by the visible region of the electromagnetic spectrum. The transmitted light, in fact the color of the complex ion, is the complementary color of the absorbed light. Thank you for watching this video. If you feel this video is helpful, then kindly like and share it. If you have any queries, please feel free to write me in my email ID.